Section 2, Non-Equivalent Groups Designs. The learning objectives for this section are 1. Describe the different types of non-equivalent groups quasi-experimental designs. And 2. Identify some of the threats to internal validity associated with each of these designs. Recall that when participants in a between subjects experiment are randomly assigned to conditions, the resulting groups are likely to be quite similar. In fact, researchers consider them to be equivalent. When participants are not randomly assigned to conditions, however, the resulting groups are likely to be dissimilar in some ways. For this reason, researchers consider them to be non-equivalent. A non-equivalent groups design, then, is a between subjects design in which participants have not been randomly assigned to conditions. There are several types of non-equivalent groups designs we'll consider. Post-test only non-equivalent groups design. The first non-equivalent group design we'll consider is the post-test only non-equivalent groups design. In this design, participants in one group are exposed to a treatment, a non-equivalent group is not exposed to the treatment, and then the two groups are compared. Imagine, for example, a researcher who wants to evaluate a new method of teaching fractions to third graders. One way would be to conduct a study with a treatment group consisting of one class of third grade students and a control group consisting of another class of third grade students. This design would be a non-equivalent groups design because the students are not randomly assigned to classes by the researcher, which means there could be important differences between them. For example, the parents of higher achieving students or more motivated students might have been more likely to request that their children be assigned to Miss Williams's class. Or the principal might have assigned the troublemakers to Mr. Jones's class because he's a stronger disciplinarian. Of course, the teacher's styles and even the classroom environments might be very different and might cause different levels of achievement or motivation among the students. If, at the end of the study, there was a difference in the two classes' knowledge of fractions, it might have been caused by the difference between the teaching methods, but it might have been caused by any of those other confounding variables. Of course, researchers using a post-test only, non-equivalent groups design can take steps to ensure that their groups are similar as possible. In the present example, the researcher would try to select two classes at the same school where the students in the two classes have similar scores on standardized math tests and the teachers are maybe the same sex, close in age, and have similar teaching styles. Taking steps like this would increase the internal validity of the study because it would eliminate some of the most important confounding variables. But without true random assignment of the students to conditions, there remains the possibility of other important confounding variables that the researcher wasn't able to control. Pre-test, post-test, non-equivalent groups design. Another way to improve upon the post-test only non-equivalent groups design is to add a pre-test. In the pre-test, post-test non-equivalent groups design, there's a treatment group that's given a pre-test, receives a treatment, and then is given a post-test. But at the same time, there's a non-equivalent control group that is given a pre-test, does not receive the treatment, and then is given a post-test. The question then is not simply whether participants who receive the treatment improve, but whether they improve more than participants who did not receive the treatment. Imagine, for example, that students in one school are given a pre-test on their attitudes towards drugs, then are exposed to an anti-drug program, and finally are given a post-test. Students in a similar school are given the pre-test, not exposed to an anti-drug program, and finally are given a post-test. Again, if students in the treatment condition became more negative towards drugs, this change in attitude could be an effect of the treatment, but it could also be a matter of history or maturation. If it really is an effect of the treatment, then students in the treatment condition should become more negative than students in the control condition. But if it's a matter of history, for example, news of a celebrity drug overdose, or maturation, like improved reasoning, then students in the two conditions would likely show similar amounts of change. This type of design doesn't completely eliminate the possibility of confounding variables, however. Something could occur at one of the schools, but not the other. For example, maybe a student drug overdose. So students at the first school would be affected by it, while students at the other school would not. Returning to the example of evaluating a new measure of teaching third graders, this study could be improved by adding a pretest of students' knowledge of fractions. The changes in scores from pre-test to post-test would then be evaluated and compared across conditions to determine whether one group demonstrated a bigger improvement in knowledge of fractions than the other. Of course, the teacher's styles and even the classroom environments might still be very different and might cause different levels of achievement or motivation among the students that are independent of the teaching intervention. Once again, differential history also represents a potential threat to internal validity. If asbestos is found in one of the schools, causing it to be shut down for a month, then this interruption in teaching could produce a difference across groups on post-test scores. If participants in this kind of design are randomly assigned to conditions, it becomes a true between groups experiment rather than a quasi-experiment. In fact, it's the kind of experiment that Eisnet called for, and that has now been conducted many times to demonstrate the effectiveness of psychotherapy. Interrupted time series design with non-equivalent groups. One way to improve upon the interrupted time series design is to add a control group. The interrupted time series design with non-equivalent groups involves taking a set of measurements at intervals over a period of time, both before and after an intervention of interest, in two or more non-equivalent groups. Once again, consider the manufacturing company that measures its workers' productivity each week for a year before and after reducing work shifts from 10 hours to 8 hours. This design could be improved by locating another manufacturing company who does not plan to change their shift length and using them as a non-equivalent control group. If productivity increased rather quickly after the shortening of the work shifts in the treatment group, but productivity remained consistent in the control group, then this provides even better evidence for the effectiveness of the treatment. Similarly, in the example of examining the effects of taking attendance on student absences in a research methods course, the design could be improved by using students in another section of the research methods course as a control group. If a consistently higher number of absences was found in the treatment group before the intervention, followed by a sustained drop in absences after the treatment, while the non-equivalent control group showed consistently high absences across the semester, then this would provide superior evidence for the effectiveness of the treatment in reducing absences. Pre-test, post-test design with switching replication. Some of these non-equivalent control group designs can be further improved by adding a switching replication. Using a pre-test, post-test design with switching replication design, non-equivalent groups are administered a pre-test of the dependent variable, then one group receives a treatment while a non-equivalent group does not receive a treatment. The dependent variable is assessed again, and then the treatment is added to the control group, and finally the dependent variable is assessed one last time. So as a concrete example, let's say we wanted to introduce an exercise intervention for the treatment of depression. We recruit one group of patients experiencing depression and a non-equivalent control group of students experiencing depression. We first measure depression levels in both groups, and then we introduce the exercise intervention to the patients experiencing depression, but we hold off on introducing that treatment to the students. We then measure depression levels in both groups. If the treatment is effective, we should see a reduction in the depression levels of the patients who received the treatment, but not in the students who have not yet received the treatment. Finally, while the group of patients continues to engage in the treatment, we would introduce the treatment to the students with depression. Now and only now should we see the students' levels of depression decrease if the treatment is effective. One of the strengths of this design is that it includes a built-in replication. In the example given, we would get evidence for the efficacy of the treatment in two different samples, patients and students. Another strength of this design is that it provides more control over history effects. It becomes rather unlikely that some outside event would perfectly coincide with the introduction of the treatment in the first group and with the delayed introduction of the treatment in the second group. For instance, if a change in the weather occurred when we first introduced the treatment to the patients, and this explained their reductions in depression the second time that the depression was measured, then we would see depression levels decrease in both of the groups. Similarly, the switching replication helps to control for maturation and instrumentation. Both groups would be expected to show the same rates of spontaneous remission of depression, and if the instrument for assessing depression happened to change at some point in the study, the change would be consistent across both of the groups. Of course, demand characteristics, placebo effects, and experimenter expectancy effects can still be problems, but they can be controlled for using some of the methods that were described in Chapter 5 on experimental designs. Switching replication with treatment removal design. In a basic pre-test post-test design with switching replication, the first group receives a treatment and the second group receives the same treatment a little bit later on, while the initial group continues to receive the same treatment. In contrast, in a switching replication with treatment removal design, the treatment is removed from the first group when it's added to the second group. Once again, let's assume we first measure the depression levels of patients with depression and students with depression. Then we introduce the exercise intervention only to the patients. After they've been exposed to the exercise intervention for a week, we assess depression levels again in both groups. If the intervention is effective, then we should see depression levels decrease in the patient group, but not in the student group because they haven't received any treatment yet. Next, we would remove the treatment from the group of patients with depression. So we would tell them to stop exercising. And at the same time, we would tell the student group to start exercising. So after a week of the students exercising and the patients not exercising, we would reassess depression levels. Now, if the intervention is effective, we should see that the depression levels have decreased in the student group, now that they're exercising, but they've increased in the patient group because they're no longer exercising. Demonstrating a treatment effect in two groups staggered over time and demonstrating the reversal of the treatment effect after the treatment has been removed can provide really strong evidence for the efficacy of a treatment. In addition to providing evidence for the replicability of the findings, this design can also provide evidence for whether the treatment continues to show effects after it has been withdrawn.